So in this video, let us continue with antiderivatives of exponential functions. This is where we left off last time. So let me remind you guys, antiderivatives work exactly the opposite of derivatives. If you guys recall how to take the derivative, e to the x is the easier one. If you integrate that, we'll just get e to the x plus a constant because the derivative is itself. But if we go to the next page, if we have e to the constant times x, which happens a lot in applications, for example, if you recall, the derivative is using chain rule, e to the k constant times x times the derivative of the exponent, which is just k. So you'll get k times e to the kx. That's the derivative. For the integral, or the antiderivative, would do exactly the opposite. It's e to the constant times x divided by the derivative of k times x, which is just k. So you divide by that plus a constant. So we do that quite often. Interestingly, the derivatives of integrals of logarithms are not very straightforward. In fact, we're not going to cover them. So let us just finish up with if the base is other than e with exponentials. And we're not going to discuss integral of logarithms. You need something else there to be able to integrate logarithms, some other techniques. But we can also integrate a to the power of x, which, if you recall, the derivative was a to the x times ln of a. So here we divide. So again, we just divide by ln of the base a. Or if you have exponential to the power of k times x, it's the same thing. If you put it together, we divide by ln of a, but we also divide by k, just like we did with e to the x earlier. This only works if you have a constant times x. If you have anything more involved, then you may need another technique, possibly the u substitution if it works. Okay, so you do have to think about them rather than try to memorize them or write them down. How do the derivatives, if you know how to take the derivative, you basically do the opposite for the antiderivative. So you divide by that. Okay, so here's a few quick examples. Let's focus on, let's say, 3 times e to the negative 0.2x dx. So notice 3 is a constant, so we keep that. We also keep e to the negative 0.2x. Now note, the power rule does not work in this case, so you're not actually changing the power. You're not increasing it or decreasing it. You're keeping it constant. But then you divide by derivative of the exponent, which is just negative 0.2. plus a constant, and then you try to simplify as much as you can. 3 divided by negative 0.2, that's negative 15, e to the negative 0.2x plus a constant. Okay, so that's how it works basically. If you're trying to integrate 10 to the x, for example, then you have it itself, 10 to the x. Then again, instead of multiplying by ln of 10 like we would with the derivative, you divide by ln of 10. Okay, and ln of 10, do not confuse it with ln of e. That's actually not 1, it's some constant. But you can keep it that way. All right. And then here is one more example. I think that was from the earlier section. If you have a t in denominator, remember that had to do with the ln. Notice how division, we don't know how to perform the division for the integral, but you can actually separate the two terms. So you can have 1 over 4t plus 2t cubed over 4t. If you simplify, you'll get 1/4 t to the negative 1 power. And you'll also get 1/2 t squared. So how do we integrate it? So if you have 1/4, that's a constant. So you keep that. The antiderivative of t to the negative 1, or any variable to the negative 1 power, is actually ln. Don't forget the absolute value, so the domain is the same. So ln of absolute value of t plus, now we can integrate 1/2 t squared. We'll keep the 1/2, that's a constant. And t squared becomes t cubed over 3. And the last step would be to do this multiplication right here. So we'll have 1/4 ln of absolute value of t plus t cubed over 6 plus a constant. Okay. Business applications, we discussed it a little bit last time, but the business applications are, if you know the cost function, for marginal cost function, you can find the actual cost. Now note, you have to have some information because we're not going to have plus a constant on the application. So you have to have either the fixed cost, or if you have cost, if you know cost of, let's say, 5 items, that would be C of 5. Fixed cost would be C of 0, and so on. So if you know marginal cost, you can integrate. As usual, I'll just discuss this one problem. You would integrate it. That's integral of 4x minus 5 dx. So you would integrate it and you would have a plus constant as usual. Let's try to simplify this. How do you find the constant? Well, if you recall that fixed cost, if you don't sell, that's cost of 0 items. That's before you have any items manufactured. That's $8. So you can plug in 0. Most of the time, all the zeros would go away unless you have exponential. But you have 2x squared minus 5x. Those would go away. So you'll just end up with a C, capital C, so you'll get 8. So the answer would be 2x squared minus 5x plus 8. So basically, you take what you had for C of x and you set it equal to C of 0, which is 8, and you solve. Same thing we have with exponential here, which is earlier, but let me demonstrate that. If we have marginal cost, you can integrate it, 0.03 e to the 0.01x. So to integrate it, again, you keep a constant. You keep exponential exactly the same, but then you divide by derivative of 0.01x, which is just 0.01. So 0.03 divided by 0.01, that's just 3, e to the 0.01x plus a constant. Notice the fixed cost is just C of 0, so notice you plug in 0 into your function plus a constant, so we're trying to solve for it, which you can simplify, e to the 0, that's 1, so that does not go away. So you have to account for that. So that's 3 times 1 plus a constant equals to 8. So you'll solve for constant in here. In this case, it's going to be 5. So it's not exactly the same as the fixed cost. So you cannot assume that. You actually have to plug it in and solve for it. So you'll get the final answer would be 3e to the 0.01x plus 5. And I think that's it. Well, the other application is very, very similar. In fact, let's go over that real quick. Pardon me if you sometimes hear noises. I have windows open and where I'm working in my office here. So once in a while you'll hear cars passing by. So just pardon the extra noise. So with the revenue, if you have marginal revenue, it's exactly the same. So if you have marginal revenue, we can integrate it. And again, the integral would be plus a constant. Now with the revenue, it's easier to recall that if no items are sold, then the revenue is 0, which means R of 0 is 0. So if you can plug in R of 0, everything will give you 0 except the constant, but that's also 0 because R of 0 is 0. And so the actual revenue would be just 175x minus 0.01x squared minus 0.01x cubed. And you can find the demand function. So this is sort of working the opposite. I believe normally before we had the demand function and we had to find the marginal revenue. So we had to build the revenue and so on. This is a backwards equation. We had the marginal revenue. How do we find the demand function? Well, once you find the actual revenue equation, the demand is R of x equals to P times x. So the demand, the price equation in terms of x, is equal to revenue divided by x. So you can divide the revenue by x, and that's how you'll get the demand function, which is 175 minus 0.01x minus 0.01x squared. Okay, and I think maybe this is the last one with the rate of the monthly text messages. I think the idea is exactly the same. You just have to be careful with the units, with the billions. But I think the idea was exactly the same. Well, here, I think it was that we were told that the approximate rate of change of monthly text messages is given. Now, in 2005, so this is since 2000, in 2005, where t equals 5, there were approximately 9.8 billion text messages. So really the only difference in this problem is that f of 5 equals to 9.8. So you had to actually plug in 5 as opposed to 0 and solve for it. So you're always given some kind of condition, initial condition. Sometimes they call it initial value, but it's not always initial. It's not always 0. but this enables you to find what the constant is, so you can have any value. And I think that's it for this section.